Today, I want to talk to you about something that I call inductive flyback. And it's an old term. Flyback is an older term. Some of you might heard it as inductive surge or inductive kickback. But when we're wiring inductive loads to a programmable logic controller, or really to any microcontroller that uses solid state switches to turn outputs on and off, we have to protect those switches. So I want to talk to you about inductive flyback protection. So let's take a look at current flowing through a wire. So I just got a piece of wire here, and when current flows through a wire, we want to ask ourselves a question. What happens in and around that wire? So I got current flowing through a wire. What's happening in and around the wire? Well, first of all, the wire is going to start to heat up. Now, if it's the right gauge, it shouldn't get even warm to the touch, but there'll be some heat generated. There's going to be a small voltage drop due to the resistance of the wire, and it's going to be very small, but it's going to depend on the length of the wire also. The longer the wire, the more resistance, but again, it's very small. And then there'll be a magnetic field that forms around the wire. So anytime current passes through a wire, I get some heat, I have a resistive, so I have a very small voltage drop, and I get a magnetic field around that wire. So now let's think about a magnetic field. And let's think about the effect that it has on current flow in a wire, or vice versa. So if we move a wire through a magnetic field, we are going to create a current flow in that wire. So I have a fixed magnetic field. If I move a wire through that magnetic field, I will get a current flow in that wire as long as I keep moving it through the field. Now, if I take that same piece of wire, or that same wire, and I move the magnetic field over the wire. So if I move the magnetic field over the wire, I will get a current flow in that wire. So now I'm moving the magnetic lines, or the magnetic field, over the wire, and I get a current flow in that wire. So now let's talk about inductors. You're going to be probably wiring some relay coils, some solenoids, some inductive loads to a programmable logic controller, or a microcontroller like an Arduino or a Raspberry Pi, or some other controller. But we're focused today on programmable logic controllers, PLCs. So here's a diagram or a drawing of a coil, an inductor, with a simple toggle switch attached to it, which is going to apply DC voltage. When I apply DC voltage, so when I close this switch, current starts flowing in the inductor. And as soon as current starts flowing in the inductor, I get a magnetic field built up around that inductor, and a polarity forms. So to turn the switch on, this magnetic field starts to build up, and it's there as long as the switch is closed. I always like to say that, and I got this from an engineer I used to work with years ago. He was a really intelligent man and had a unique way of describing things. But and he says this, and I also like to say this, that inductors absolutely love to have magnetic fields on them. Once they get that field on them, they are absolutely in love with having that field. So much so that they don't want to give that field up. They don't want to let it go. But we know that, if we open the switch, we're going to stop the flow of current going to that inductor. And since we stop the flow of current going to that inductor, the field is going to start to collapse. As the field starts to collapse across an open circuit, across an open switch, so there's no circuit here, it's an open circuit, the field's going to collapse. Well, I've got a magnetic field moving across wire. The laws of physics say that if I've got a magnetic field flowing across wire, I have a current flow in that wire. But the switch is open. So the resistance in the circuit, or the impedance of the circuit, is infinite. So as the field starts to collapse when the switch is open, I get a current flow in the inductor, and it's in the opposite polarity. So the polarity is going to flip. And when the polarity will flip, the field is collapsing. We can figure out what the voltage is going to be because there's a current flowing. The laws of physics tell us that. There's a current flowing in an open circuit. Has to be. We can calculate the voltage using Ohm's law. You can use E equals I times R or V equals I times R, depending on how you were taught the equation looks. I was taught voltage was E. I don't know when they changed it to V. I'm not going to get on my soapbox about that. Voltage is energy. It should be E. But anyway, E is equal to I times R. So voltage is equal to the current times the resistance. Well, the resistance is infinite. It's an open circuit. So E is equal to I times infinity. Well, it doesn't really matter what the current is because anything times infinity is going to be infinity. Which means that when that switch opens, the field is going to collapse, the polarity is going to reverse, the voltage is going to go to the ceiling to try to maintain that field. Unfortunately, what it's going to do is it's going to arc across that switch. So if I open it, it arcs across the switch, the polarity reverses as the field collapses, it arcs across the switch, and once it arcs, it dissipates the energy. Now that mechanical switch can probably take that abuse for quite some time before it finally fails. You may have to, if it's a relay contact, you may have to clean the carbon off of it from time to time. Switches are self-wiping usually, so they really don't need a lot of cleaning or maintenance. However, eventually that switch is going to fail just from that getting hit by that high voltage. Folks, this is how the ignition systems in your car work. You ever wonder, how do you get a spark or an arc across a spark plug with 12-volt battery? It's because of the coil. All cars have an ignition coil. Now, years ago, they used to have a set of points. They don't use points anymore because it's electronic ignition, but it's easy to explain when you use points. Points is nothing more than a set of contacts. And as the cam rotated, the contact would close, put voltage on the coil. When the points opened, the voltage on the coil went to the ceiling and it arced across the spark plug to ignite the fuel. It's exactly the same concept, only this time we need to protect our switch, our spark plug, so that it doesn't arc across it. Because when we wire this, I'm sorry, I got ahead of myself, but let's do a summary. So we close the switch, current starts to flow, a voltage is developed across the coil, which then creates a current, a magnetic field to build up. When the switch opens, the current stops flowing, magnetic field starts collapsing, the voltage polarity reverses, it's an open circuit, current's flowing, the voltage goes to the ceiling and arcs across a set of open switches. I have a little note here that says it takes approximately 5,000 volts to arc across about a 1/16 of an inch, which is 1.58 millimeter, in dry air. So now we're going to replace that switch. We have to wire these inductive loads to a PLC or some microcontroller board output, which means that that mechanical switch is going to be replaced with a solid state device. Now I'm showing in this diagram a transistor, but it can be any solid state device that can be acting as a switch. It could be a transistor, it could be an FET, which is a field effect transistor, it could be any other type of solid state device. So this time, instead of having a mechanical set of contacts that literally open, I have this solid state device. Now, when I send a logic, the base of this, or the actuator of this device, is going to receive its signal from the processor, from the CPU. So when the CPU sends a logic 1 to that device, it turns it on. It forward biases the device such that current will start flowing in that solid state device. And when current flows through the device, it flows through the inductor, the field builds up, and I get the polarity of plus to minus. So everything works the same, just as when I closed the mechanical switch. The difference this time, though, is that when the CPU sends a 0 to that base to turn off the transistor, there's no real mechanically open circuit for that arc to flash across. I'm still going to have a field collapsing. I'm still going to have a reversal of polarity. I'm still going to have a voltage that goes to the ceiling. Only this time, it's going to go through that solid state device. So I'm going to send a logic 0. The field collapses, the polarity reverses, and if you saw it, I had an arc from collector to emitter. Now, you know what? That solid state device might be able to take that voltage spike a few times. You know, you open it, it might go, oh, and it'll still work. The next time it'll go, oh, it'll still work. And it may work for, a while. But eventually, that device is going to fail. It can't continuously take that abusive hit of high voltage. So, we have to wire inductors to these circuits. So we have to have a way to protect the switch, whether it's a mechanical switch or a solid state switch, from these high voltage arcs. So we need a way, we need a method for this protection. So we know that when the switch is open, the magnetic field collapses, the voltage across the coil reverses polarity, and the voltage spikes up to thousands of volts. So it would be really nice to find a device that can detect the high voltage and or the reverse in polarity without affecting the operation of the coil when the switch is closed. Well, we do have such a device, and that device is called a diode. A diode will only conduct in one direction. It's a solid state device, but it will only conduct current in one direction. So this and this and this are the schematic symbol for a diode. A diode has two elements. It has an anode, which is this side of it, and it has a cathode. A typical diode physically looks like a little black cylinder with leads and a silver band on it, and that band marks which lead is the cathode. When the anode of the diode is approximately 0.7 volts more positive than the cathode. So here the anode is more positive, a bigger positive than the cathode. The diode will be forward biased, and the diode will start conducting current. So current will flow, and I want you to make sure you see this is conventional current flow. The arrow on solid state devices points in the direction of conventional current flow. If the cathode becomes more positive than the anode, the diode is now reverse biased, and no current will flow. So that sounds like a device that'll work. Let's place this device across the coil. So here I have the same circuit with the transistor being used as the switch, and I put a diode in the circuit right across the coil. The CPU is going to send a logic 1 out to the switch. The transistor turns on, and I get current flow. However, the anode of this diode is more positive than the cathode. Therefore, the diode is forward biased. Therefore, the diode is conducting current. There's a 0.7 volt drop across it, and there won't be enough voltage across the inductor to energize the inductor. So let's turn this off, and let's rotate the diode in the other polarity. And then we'll turn this on again. Now that we turn this on, this time it works the way we expect it to work. Current starts flowing through the transistor. The cathode this time is more positive than the anode, so the diode is reverse biased. It will not conduct current. The current flows through the inductor and the field builds up. So this now works exactly the way it did without the diode. Close the switch, current flows, field builds up. Inductor's happy. Now we're going to turn the transistor off. The same things are going to happen. Current stops flowing in the circuit. The field starts collapsing. The voltage polarity reverses. However, now that the diode's in there, since the field is collapsing and the polarity reversed, now the anode is more positive than the cathode. The diode is now forward biased, goes into conduction, current flows through it, and it clamps that high voltage spike to 0.7 volts. Won't hurt the solid state switch. It suppressed that voltage spike. Any 1N4000 series diode should work across those coils. A 1N4003 through 1N4007. Any of those should work. And you also, when you mount that diode, you want to get that diode as physically close to the coil as you can get it. The further away you go from the coil, the less effect it's going to have. So you want to get them as close to the coil as you physically can get them. So this will solve the problem for switching DC inductors. But what about AC inductors? I have AC coils too, and they have to be protected because they will also have inductive flyback. But if you think about it, I can't use a diode for this. I've got an AC signal, which means it's a sine wave, which means the field is going to build up, and as the sine, it's going to start collapsing, it's going to go through zero, and then it's going to build the other direction, and then it's going to, as the sine wave's going, and it's going to keep building, collapsing, building in the opposite polarity, collapsing, building in the and going back and forth like this. Well, it's continuously changing polarity, and there is no way I can determine the polarity of that AC voltage when I turn that switch on or off. If I would use a diode, the coil would only be energized every half cycle because the diode would be conducting on the other half. And that may make it so that the diode doesn't really work, or the inductor won't really work. So I have to have another way of protecting that particular switch from AC flyback. That device is called a metal oxide varistor, an MOV. Here's a typical picture of an MOV. That's typically what they look like. They come in different colors, sizes, shapes, thicknesses, but that's typically what they look like. This is the electrical symbol for it. They have no polarity. What an MOV has is a voltage rating. And it's rated such that this voltage is the voltage that the device or the MOV will start conducting current, and it will clamp the voltage across that MOV at that voltage. So if I have a 120 volt RMS coil, I can put an MOV across there. Now what I do to pick the voltage of the MOV, and this is only my rule of thumb, I think there is probably a scientific method for solving this, but what I do is I will take the peak to peak voltage of my AC signal, not the RMS. If I have 120 volts, that's RMS. If I have 220 or 240 volts, that's RMS. I want to calculate what that is peak to peak. And then I'm going to take the peak to peak voltage and I'm going to double it. So let's say 120 volts. I'm just going to guess at a number here. I think peak to peak is around 160 some volts, and really I'm just pulling that out of the air right now. If I double that, I get 320 volts. So I'll go out and I'll look for an MOV, and I may not find 320. They may have a 300 volt one or a 400 volt one. You know, either one of those will work. So that when you open the switch, the voltage across the coil will get no higher than the rating of the MOV. And 300 and 400 volts is not enough to arc across any switch. So an MOV can be used on AC coils, and again, you want to mount them as physically close to that coil as you can possibly get them. So I hope this helped. Every single inductive load that's wired to a PLC or to a microcontroller that has digital outputs on it that control inductive loads should have flyback protection on it. So I hope this helped, and I'll see you next time.